All right, everybody, we are about to jump into systems of equations and matrices. There's going to be a study of matrices here. So we'll see how that all fits in and what's a matrix and all that kind of stuff later. But first, um, something to say about this. First of all, we're going to be solving systems. And second of all, the ones we're going to do are going to be linear equations. Okay, so that's what our emphasis is going to be on for this next little bit. How do we solve them? What does it mean to solve? So we'll look at that in a second. And then what does it mean to solve a system? What is a system? Okay, we know how to solve a linear equation by now, but we don't know what a system is. We don't know how to solve one. And by the way, we're dealing with linear equations, but there are other kinds of equations out there like quadratics and things like that we'll talk about, right? Okay, so first of all, we need a definition. What is a system of linear equations? Or let's just say a system of equations. A system of linear equations is two or more equations examined as a group normally with the goal of finding points they have in common. And for our purposes, we are going to call that point or points that they have in common the solution. Okay. And again, it's going to be the solution to the system. So, you could get a little confused here, but I don't think it's going to be bad. So, let's just take a look and see what's going on. So, for instance, let me give you a system of equations. We'll look at this example first. 2x plus y equals 32. That's one linear equation. We've dealt with those things before. And x plus 3y equals 36. All right. So first of all, normally we're going to have this little curly Q bracket out in front of those that tells us, hey, this is a system of equations. For sure, when we see that curly Q bracket, we know that. Not always. Sometimes you'll see they'll just hand out two little equations and say, here's a system. Okay. I know that these are both linear, and if you'll go back, I know it's been a while, but in exam 1, we talked about how some equation is linear, and it's linear because the highest power on x and y is a 1. Okay, 1. So when we talk about this, we can look at the exponents, right? Here we've got 2x. It's really raised to the first power. I don't have to write that. Most of the time we don't. But what is the biggest power on x here? It's a 1. We don't have ax squared plus bx plus c, which would throw us into quadratic format, right? Okay. And same thing here on the y. It is actually important that we have a 1 also on the y, although normally we just think about the x guy, because what if I had a y squared on something? Well, if I had y squared on something, to get the y by itself, I would need to take the square root, and all of a sudden my exponent on the x wouldn't be a 1 anymore, right? It would be a square root, okay? So it would be a 1/2. Same thing here on this second equation, x to the first 3y to the first. That's how I know that the power, I shouldn't even say highest. Let's just say the power. Let's mark out that word highest. I'm sorry. let's say that the power on the x and the y is is a 1, because like I just said, you don't want a 1/2 either. You don't want this to be some weird radical. You don't want this to be irrational. None of that other stuff that we've dealt with, right? So we want these to be just straight up linear equations, and they both are. Okay. Now, in the past, what we would have done is we would have said, hey, if we want to solve, and I'm just going to pick the second one, x plus 3y equals 36 for y, and then find for us solutions for this guy would be x-intercepts, right? If we want to do that, okay. We might even want to find some y-intercepts. Those would be points that are on the graph. Those are points on the graph. Okay, we can do that. In fact, remember, we can do x-intercepts really quickly because we can say, make the y be 0. Well, if the y is a 0, then the x is a 36, right? And we could find y-intercept by saying, let the x be 0. Well, then y would be 12, right? So we can find those x-intercepts really quickly. But what we would normally do in a situation like this is we would get the y by itself. So I'd subtract the x off both sides. 3y equals, it's negative x plus 36. And then we would divide by 3 on both sides, right? And we'd come out of this with y equals negative x over 3, or you could say negative 1/3, okay, x, plus, and 36 over 3 is a 12, right? Okay, now that's not my solutions to this equation. What we would then do is come in and say, okay, what if x was, let's pick nice numbers here. If x is 0, 0, negative 0, 0, divide by 3 is 0, 0 plus 12, I get 12. Hey, that's the y-intercept we already talked about, right? Okay, let's pick another number that's going to be nice. Let's do 3. Okay. Negative 3 divided by 3 is negative 1 plus 12 is 11. That's not bad. Let's do one more. Let's do, what if x is 6? Notice I'm picking numbers that I know will divide evenly with the 3 so that I get nice, pretty whole numbers. If you want to do x equals 1 and deal with negative 1/3 plus 12, be my guest. But I'm probably going to pick nice, pretty numbers, right? So negative 6 over 3 is negative 2 plus 12 is 10. Okay. And all of these numbers over here are solutions to the equation. Now, what do we mean by that? If you plot that graph, plot this guy on my calculator, you can graph it by hand also, but I'm going to use my calculator because I have it and I want it to use it. Okay, so I already have stuff in my y. I'm going to clear that out. Y equals, I'm going to put parentheses, negative 1 divided by 3 times the x, negative 1/3 x, right? Okay, plus the 12, right? Okay. Now, we should already have a pretty good idea of what this guy looks like, right? In fact, it's got the y-intercept at 0, 12, and this is a what? Negative slope, and these numbers are going down as I go out there. So this is going to look something like this, right? Okay, I'm not sure exactly what it looks like, but it's going to be decreasing and so on. So because I know I need to be up to 12, my guess is that my window is at a 10. Oh, it's not even at a 10. So let's make our window a little bit bigger. I'm going to go to negative 10 to 10 on my x values. Oh, look, and the y values were really big the last time we used this calculator. So let's go, I want my y values to go all the way up to 12. So I'm going to go negative 10 to, let's say, positive 20. Okay, and that should get for sure this point in my graph that I can see. So let's see it. All right, there it is. Okay, and so it is crossing here at 0, 12. If you want to, you can trace, and it tells you, hey, that point there, it's 0, 12. Okay, we knew that. And if we follow this guy over far enough, Mm, here's 3. It's not quite exact. 3, 2.87, I got 11.04, and at 3.03, I've got 10.98. It looks like 11 to me. Again, that's a pixel issue. If you really, really want to check it, you can always go into your table and see what's going on there. To get to table, I need the second value. I'm sorry, the second graph button. And here we go. There's 11, and the actual Y value is 11. I'm sorry, 3 and 11. 6, and I've got 10. 9, and I'll have 9. Okay, so you can see those points. You can play with your calculator. If you don't know what you're doing with your calculator, then maybe take a second to learn it, but it's not going to be that important for us for the test. So I just want you to know all of these points are solutions to this equation. Okay, that's the second equation I had. But my question is, what if I took this other equation? So let's see it. Um, the other equation is 2x plus y equals 32. Well, again, I can't stick that on my calculator like that. I need to solve for y. This one's not bad at all because I'm just going to subtract the 2x, right? So y equals negative 2x plus 32 is that guy, right? Okay, and again, interestingly enough, I see that this one is also a negative slope right here, right? It's going down -2. That one was going down -1/3. But the y-intercept is 32, right? So if I want solutions for this equation, it's going to look like stuff like put in a 0 for x. 0, 32 is that y-intercept, right? Let's try to pick the same kind of numbers. Put in 3 for x. -2 times 3 is -6. -6 plus 32 is 26. And 6. If I put 6 for x, I get -2 times 6 is -12 plus 32. I get a 20. Okay, so it's still coming down. It still looks like this, but I'd say it's a lot steeper. Okay, if that makes sense, because the slope here is -2, whereas the slope there was only -1/3. I'm going to graph that guy. So for just a second, I'm going to turn this graph off. You don't have to know how to do that, but what I'm doing is I came over on top of the equal sign and I hit enter. Right now it's on, and I know that because it's dark. Okay. When the reason I want to turn it off is because here in a second I'm going to put in, let's do it right now, -2x. And again, make sure you're using the negative button down here at the bottom. If you have a graphing calculator, don't use the minus sign. So -2x, and it's plus 32. And what I want to do right now is I want to graph this one. See, they're both on. I can see they're both dark. I want to graph the second one, but not the first one. So that's why I came up here on top of the equal sign. See, it's flashing. And I hit enter, and look, now it's not dark anymore. What that tells me is the calculator is going to graph y2 here and ignore y1. So let's see what that graph. Oh, before I do it, what about these values? Earlier, I needed 12 on the y value, but now I need 32. So I'm going to go into my window and say, hey, I need that Y max a lot bigger. Let's go all the way to 40. Let's go -40 here to 40. And I'm going to count by, say, tens because I don't want a lot of little hash marks in there. All right. I still don't see where it's crossing the x-axis out here. If we need to, we'll make it bigger. But see, it made this one red. That's just a function of this particular calculator. It does colors. My old calculator does not do colors. They would both be black. But it's kind of nice because when I get there in a second, I can see what's going on. I'm going to trace this and see, look, the 0, 32 with the trace button right here. Okay, 0, 32. And as I go down, sure enough, it's a negative slope. So as I get down here to 3, it's not exact again. It's a little bit bigger than 25.9, right? Okay, again, I can go into the table with just second graph. and I can see the exact values if I want to. 3 is indeed 26. 6 is indeed 20, and so on and so forth. 9 is 14. So I can see those things. Now, all of these are solutions to this equation. Okay. But the problem is when you look at this, is 032 a solution to both of these equations? No, Dr. Webster, it's not, right? Because up here it's 012, down here it's 032. Those can't be, we can't have two zero values, zero with a y value, or I wouldn't have a function, right? These are linear. These are nice and straight, right? Oops. I already got off of there, but they're nice and straight. So they're not going to loop back around or do anything crazy. Okay. So when I said earlier, let me turn this guy back on, the first equation. When I said earlier, excuse me, normally with the goal of finding points they have in common, and we're going to call that the solution to the system. Okay. What I think is these two equations, they're both negative, but at some point they're going to cross. Okay. And then I'll have a point that they have in common. And indeed, that will be a solution for my system. So I've turned both of them on. I'm going to graph them both. And we can see, hey, they're going to meet, but it's right outside of the window here. So let me go back and change my X window one more time. Let's go -10, let's say to 30. And again, let's go up by, say, 5. Let's see it. There's my blue guy. There's my red guy. Hey, look, they do indeed cross in one point. Okay. They have one point in common. That's the solution to the system. Okay. Now, the trick here is how the heck am I going to figure out exactly what that point is? Okay. Your calculator does do some cool stuff where you can calculate an intersection and things like that. If you know how to do it, it's second, and then above trace, you see calculate. We're looking for intersection. So sure enough, it says what's on the left side. Oh, I'm sorry. What's on the first curve? What's on the second curve? Do you want me to guess? And I say yes. And it says, okay, we think it's intersecting at 12 and 8. Okay. And it's just kind of extrapolating. Okay. If I come from there to there and there to there, where do they meet? Okay. So the calculator knows. Okay. 12 and 8. That's what it thinks is my system. Okay. Um, we're currently solving an equation or a system of equations by graphing, by looking at this graph. But I would like to make sure that it really is doing what it says it's doing, that they really are crossing. Now, again, these are linear, so they're not going to cross back on themselves or anything else. And we can tell, hey, as this goes farther out, these are getting farther away, right? And here they're farther and farther away. So they're only touching in one point, and that's going to be important, okay? Two lines, if they have a unique system solution, are going to have one point in common, and that's it. Okay. So I'll give you some pictures of that in a second, but that's going to be really important. So hold on. Let's do a little math and make sure this works. On the graph, we see solving by graphing. Okay. My calculator says that they cross at the point 12, 8. All right. And again, these kind of look like this, right? One of them's going like this. One of them's going down a lot more steeply. And we're looking for this point right here. And the calculator is telling me it's 12, 8. We're going to check, but that's what the calculator is telling me. And if all I'm doing is graphing these to see, I probably actually will almost always go to my calculator because it's just going to do a lot more thorough job of graphing and a lot prettier job of graphing than I do, right? Okay, but let's check it. If it's a solution, if this point is a solution to the system of equations. Okay, what was my system again? Remember up here, We had 2 equations. This was my system that had the curly Q bracket on it, right? So, if this point is a solution to the system of equations, then the point 12, 8 will work in both equations. Okay. Most of the time, we're going to deal with 2 equations. If we were being more advanced, we might have more than 2, but I'm saying in both because there's only 2 here. So it would work in both equations. Okay. Now, what does it mean to work? Okay. To work means I get a true statement. Okay. And we'll see this in a second. Okay. To work means I'm going to get a true statement. So I'll be able to put a check mark beside both of them and say, yep, sure does work. Okay. That's what we mean. Okay. So let's look. 2x plus y. That's my first equation. 2x plus y equals 32. Okay. So what we want to know is 12/8 a solution to this equation? So it's not one that I got, right? Because whenever I was working, let me come back to my work real quick. Whenever I was picking points, I didn't get all the way out to 12, right? On either one of these, I only went to 6. So I don't know if it works in either one of those. Okay. And by the way, one of the ways you can solve by graphing is just keep on putting points until you see, oh, they're together. Okay. Now that's not very efficient, but it will work. So is 12/8 a solution to this equation? And how do I know? Well, I know because what I'm going to do is I'm going to plug it in. Plug the point into the equation to check. Okay, that seems straightforward enough. In fact, I think you have some homework questions that just ask you this. Is this a solution? And you just got to plug it in. Okay, so let's see. I've got 2 times the x value they want me to check is 12 plus the y value they want me to check is 8 equals 32, and I'm going to put a question mark. Okay, that's what I'm trying to find out. And sometimes in the text or in the homework, you might see them put a question mark right on top of that equal sign. Okay, and so let's see. 2 times 12 is 24 plus 8 equals 32. And hey, yeah, that does work. Okay, check. Okay, so that means I'm checking this point inside of that one equation. If it works, if it gives me a true statement, I'm gonna write that right here. True. Okay. If it works, then hey, we're good. Now, what if I had put something in and it didn't work? For instance, um, on this one, we'd said 012 doesn't work, right? So let's just check. Is 012 a solution to this equation? Same one. Not the other one. We know it works in the other one. Okay. 2x plus y equals 32. I want to know, does it work here? Okay. Well, again, how do I know? I plug it in. 2 times 0 plus a 12 equals 32. Question mark. We're not saying it does. We're saying, does it? Okay. So put it in and say, oh, 2 times 0, that's 0. 0 plus 12, that's 12 equals 32. Is that true? No, Dr. Webster. No, it's not true. Okay. That is not a true statement. That is false. So the answer is no. Okay, so I knew already that 012 wasn't going to work there because I have for that equation 032 as a point, right? That was its y-intercept. But just in case, we can always check, right? Okay, so this point though, 12/8, sure enough, it's a solution to this equation. So the question is, am I finished? No, Dr. Webster. Why not? Okay. If this point is a solution of the system of equations, I didn't say just one of the equations, I said the system, both of them, then 12(8) will work in both of the equations. Okay. Now, if they had said, is 0, 12 a solution to the system of equations? You would say no, because it doesn't work in one of the equations, so it doesn't matter if it works in the other one, right? If you find one false statement, then you're done. But here, for this point, 12(8), it did work in this equation. So because it worked in one, I do need to check the other. Okay, so what's my other equation? Okay, so check 12(8). In that equation was x plus 3y equals 36, to see if it works in that equation also. Okay, we got to check it. We don't know. Okay, so we need to check it. Okay, 12(8). We're going to stick it into this equation. So what are we saying? 12 for the x, 12 plus. We've got a 3 times. What are we putting in for the y? 8, right? Equals 36. And we put a question mark there because we do not know if it does or not. We are checking and we will find out. Okay. So here we go. What do we got? 12 plus 24 equals 36, question mark. And sure enough, yep, it works there too. So 12(8) works in both equations. You have to check both. It is the solution to the system. Okay. So here's the deal about this. I am okay if you want to use for these graphing things, if you want to use your calculator to check, because it is a tool and we use it, and that is fine. And I use it and you can use it. What I'm not okay with is if on a test you say, oh, yeah, it's a solution because my calculator told me so. You know what? You should know this about me by now. I have to grade what you put on the paper, right? If I can't see your calculator and I can't read your mind. So if you want to get credit for it, you need to show me your work. Okay. So it's not enough to say, yep, the calculator told me so. You can use it and say, hey, let's check 12(8) because my calculator says 12(8). But then you have to go through and you have to show me where you plugged it in on this equation. Okay, it worked there. Okay, I put it in this equation. That's a true statement also. It works there. It works in both equations. So it is the solution to the system. And remember, excuse me, when we have one point like this and those two equations, they just crossed, right? They went and they touched in exactly one point. It is a unique system to this solution. Okay, or a system to it is a unique solution to this system. Sorry about that. So there's only going to be one. Okay, whenever we're doing equations of systems of linear equations. I'm sorry, my words are getting tangled tonight. Okay. Now, how is that important, or what the heck are you talking about? Let's say that I was doing some linear equation and some parabola, okay, which we know this guy is an x squared and this guy is an x plus something. We don't know. So this is linear and this is quadratic. And there's some other stuff going back there, but I don't care. Yeah, there's some plus whatevers. Okay. This is just to show you what's going on there. When I have a parabola, it's possible that I have two solutions, right? Okay. That's why I made a point of saying both of these equations are going to be linear. Okay. So, and by the way, what if it was cubic? You know what your cubics look like by now, right? So, If this was a linear and I had some cubic like this, there could be 3 solutions or 2 solutions or 1 solution. That's the max, right? But it could have more than 1 solution, okay? So 3 solutions are possible. It doesn't have to be 3, but it's possible, right? This is 2 solutions are possible. Okay. Again, it doesn't have to be 2. They don't even have to touch if I drew them right. But if I have 2 linear equations, which is what I said from the start, when they cross, they don't double back on themselves, right? So it's one unique, oh man, unique solution possible. Now there's 2 other things, 2 special cases. We'll deal with those in a little bit. I'll tell you all about them. But for right now, most of the time we're going to have one unique solution. What if they were perpendicular to each other? Like the x and y axis, 90 degrees. Okay. Well, how many times did they cross? Just once, right? Okay. It happens to cross at the origin, right? 0, 0. We know that guy. Okay. But these 2 linear equations, which this guy would be y equals 0 and this guy would be x equals 0, if we had those 2 linear equations, they only have one unique solution, right? It's not going to look like a parabola bending back on itself. Okay. So that's why I said if we have a unique solution, there's only one unique solution when I'm dealing with linear, okay? And that's what we're going to talk about in this class, so it's going to work out. Okay, let's look at a couple of others. Here's an example. I want you to do this by graphing again. Okay, so use graphing to solve. And my system is 2x minus y equals -3. And x plus 2y equals -4. All right. So what I would like for you to do, if you can, is push pause on the video, go through and either use your calculator, or if you need to, you can make an XY chart for each of these, one for the first equation, one for the other equation, and plot in points like I did for the other, right? If I put in 0, what do I get? If I put in whatever, what do I get? But it's faster and easier if you have a graphing calculator. That's why we said for this class that the TI-84 is highly recommended. If you can do that. If you can't do that, some of you know how to use, say, Desmos, or you might have a graphing calculator app on your phone or on your tablet or something like that, that would help you be able to graph these more easily. Almost all of those, no matter what we're doing, we probably have to solve for y. So to be able to do them quickly and easily. So you probably have to solve for y on both of these equations, get them in their new format, and then see if you can graph them, see if you can find out where they cross. Okay. So if they cross, they will cross in one point. All right. I'm going to push pause. I'm going to work through this and you do the same and then come back. All right. All right. So here we are. This is the question I asked you to do. This is my work. I don't know why it's so off-centered. I'm sorry. I don't know. What I did was I solved each equation for y so that I had them in the slope-intercept form, so that if you were doing this by hand and you wanted to check points, this is the easy way to figure out, oh, I should probably pick in for this equation numbers that are divisible by 2, right? So then you could pick some points and see what's going on. I did this on my calculator. You see the one is the blue is the positive slope guy here, 2x plus 3. And the red is the negative slope here, -1/2 x minus 2. I do indeed see that they are crossing in one point, and the calculator is telling me that the intersection is -2, -1. If you don't know how to do that second calculate, intersect, equation 1, equation 2, and it tells you what it is, then you'll just have to trace it and say, "Oh, I think this really looks like it's crossing at -2, -1." Okay, and then check and see. All right, so that's what I did is I put in -2, -1, and I'm looking at these, and I said, "Is -1 the same as -4 plus 3?" Yes, Dr. Webster. Okay. And is -1 the same as 1 minus 2? Yes, Dr. Webster. Okay, so I think it works in both of these equations. Okay, so I put check marks on both of those. -2, -1 works in both equations. And therefore, it is a solution to the system of equations. It is the spot where they intersect. It is the one point that we have that works in both equations. If you picked some other point, like say plug in x equals 0 here and then plug in x equals 0 here, well, that one's pretty easy, right? This one gives you the point 0.03 for my y-intercept, right? And this one gives you the point 0, -2 for my y-intercept. Are those the same? No. So the only point where they actually cross, where they have the same values, is at -2, -1. Okay. So that is the solution to that particular set of equations. Okay. Now, the graphing method is very nice because it's very visual and everybody can see what's going on. A lot of people like it. It's not my favorite, and the reason why is because it's just so stinking slow. It takes forever for me to. I've got to set these equal to y equals whatever, rearrange them. I've gotta graph them. 'em, I've gotta intersect them, I've gotta find out what the point is, -2, 1, a -2, 1, and then I've gotta check it in both equations. It just feels to me like it takes a long time, so it's not my favorite, but it is good for showing you this 2 special cases. So let me use the graphing for these 2 special cases, and then we'll talk about what's going on, and then later when you see it, when you're doing the other methods and you see this weird thing happen, you'll go, "Oh, that's because that's one of those special cases that Dr. Webster warned us about," right? Okay, so 2 special cases. So here's an example of the first kind, and it literally says graph, x plus 2y equals -4 and 2x plus 4y equals 8. That's my system. Okay, so graph those, find a solution. Okay. Well, let's do this together. So we're gonna do it the good old-fashioned way. I'm gonna try to be more half and half here. I don't know how I got so far off earlier. It's off the other direction. I'm sorry. Okay, x plus 2y equals -4 over here. I'm gonna solve for 2y by subtracting the x from both sides, right? Move the x over. And then I'm gonna divide by 2 on everything. Y equals -x over 2. -4 divided by +2 is a -2. Hey, we just saw that guy, right? Okay, so he looks familiar. That's one of the equations. And then the other one I'm going to put in right here. 2x plus 4y equals 8. Solve for 4y, get him by himself. 4y equals -2x plus 8. And then divide by 4 on all of them. Y equals -x over 2. It's 2 over 4, but I know that reduces to 1/2, right? And then 8 over 2 is a +2. All right. Hopefully, you see these 2 and you go, y equals negative x over 2, y equals negative x over 2. The only thing different is their y-intercepts, right? Okay, so that's kind of weird. Okay, and you hopefully know something about equations that have the same line. Do you? I'm sorry. Equations that have the same slope. Helps if I use my right word. Equations that have the same slope. We'll come back to that question in just a second. Hopefully you do. Hopefully you're shouting it at the thing. I know what it is. I know what it is. Okay. So here we go. I've already got the negative x over 2 minus 2 guy in there. So I'm going to leave him alone. And then I'm going to just clear this guy out and put that here. Negative x over 2. Again, remember to use your negative button way down here. Don't use minus sign. Okay. It'll give you an error plus 2 because that's what this guy is, right? Okay. So did you figure it out yet? Equations with the same slope. Let's graph this and see. What are those? Parallel lines, Dr. Webster. That's what I hear. I think these are parallel lines. So if I try to do this calculate intersect thing that we did just a minute ago, what do you think? Here's my first curve. Here's my second curve. What do you think? Are they touching? Are they ever going to intersect? If they're parallel lines don't intersect, right? So when I hit enter, it goes, ooh, error, no sign change. Now, if you don't speak calculator, that's okay. What it's telling me, and it's just telling me to quit out of there. Calculations are not detecting a sign change to give an estimated result for the allowed number of iterations. What the heck does that mean, Dr. Webster? Okay, what they're telling me is both of these have the same slope. They're going in the same direction. They're both negative 1/2. In order for them to intersect, like it would be helpful if one of them was a positive slope and one of them was a negative slope, or at least not the same slope. The same slopes are never going to touch, right? Okay, so sometimes calculator speak can be a little confusing, and your calculator might just say error and not even give you that much, right? So mine's trying to explain what the heck is going on here that we got this error. So if your calculator doesn't talk to you like this, it's okay. It probably just says error or says quit or something like that, and that's what you get. Okay, but yeah, these are parallel lines and they never touch. Right? They never ever are going to touch. So what does that mean? What is their solution? There's no solution, right? Because there's no intersection. They're not going to meet because they're parallel. So there's no solution. Absolutely. All right, so that's the idea there. So whenever I solve one of these for graphing, got the y equals, and I see they have the same slope, negative 1/2, negative 1/2. I then look at these and I be a little bit careful. Their y-intercepts are different, right? One's got a positive 2 for a y-intercept and one's got a negative 2 for a y-intercept. Because their y-intercepts are different, these are two different equations with the same slope. They are parallel. Okay. So I look at that, I go, oh, no solution. I didn't even have to graph them. As soon as I saw that negative 1/2, and these y-intercepts are different, then I went, okay, I'm good. Now, why do I say these y-intercepts are different? Because what would have happened if they had been the same y-intercept? What if they were both, let's say y equals blah, 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 minus 2? What if it was that? They have the same y-intercept, then that's the same exact line, right? Okay. And you say, oh, I would know that they're the same line. Well, not necessarily, because sometimes they don't look the same to start out with. So we'll see an example of that here in a second. But if these were the same and I just wasn't paying attention, I went to graph them. Did you see what just happened? Okay, let me do it again. Watch real closely. First, it's going to graph the blue guy. Oh, Now it knows. Now it knows, and it's like, "What the heck?" Okay, so let me trick it for just a second. See, sometimes these things are too smart for their own good. Alright, so it's graphing the blue line and then the red line, right? But whenever I change them so they have the same minus sign there, watch really closely. Blue first, then red. Blue. Look at the red coming right on top of it, right? Okay, so if you didn't see that, rewind and do it again. Mufasa. All right. So when they're the exact same line, then all of their points are the same, right? So that's the second special case. All right. So if they're the same slope but different y-intercepts, they are parallel and they will have no solution. That's one of my special cases. But special case number 2. What if they have the same slope and the same y-intercept? Then they are the same equation. So here's my example. 2x plus 4y equals 8. X plus 2y equals 4. See, those don't look alike. If you're really paying attention, you might notice that this equation up here looks like it's twice that equation down there, and that is exactly what's happening. Okay. But if you're not paying close enough attention, or you're just in a hurry, or it didn't occur to you to check for that, then what are you going to do? You're going to solve these guys for y, just like we've been doing. Okay. Get the y by itself, divide by the 4. Again, negative 2 over 4 is negative 1/2 times the x. 8 over 4, it's a positive 2. Okay, this is what I got. Okay, and that's not even what the guy looked like last time, is it? Oh, no, it is. It looked just like that. 2x plus 4y equals 8. Okay, so we're using that same one, but here we haven't dealt with this equation yet. X plus 2y equals 4. Get the y by itself. Negative x plus 4. Divide everything by 2. Negative 1/2 x. Positive 4 divided by 2 is a plus 2. And now I look at this and I go, "Ooh, hang on a second. That's the same line." Right? Absolutely, that's the same line. And what did we see just happen a minute ago? Okay. If your two equations are actually the same line, what was it? What happened? Let's see. They're right on top of each other, aren't they? They graphed right on top of each other, and how many points do they have in common? All of them, right? So they are all the same. Okay. If the two equations are actually the same line, they share all their points. They share all of their points. Okay. So how many solutions is that? Is it 1? Is it 2? Is it 5? How far does that equation go in each direction? Infinity to the right, negative infinity to the left. So how many solutions? They have an infinite number of same solutions. So that's really a weirdo, right? Okay, and it doesn't happen all that often, but every once in a while you'll see, and you'll see it in your homework. Hey, we started with two different equations here, right? They didn't look the same to begin with, but once I solved them for y equals, they look the same. They are the same line, and you know that because the slopes are the same and the y-intercepts are the same, right? Notice that's just slightly different from the one where they were parallel. They both have the same slopes, but whenever you have parallel lines, the y-intercepts are different. Okay, so we're going to have to watch out kind of pay attention. If you don't remember which one's the same slope and y-intercept, it should be, if it's both, it should be clear it's both of that it's the same line. But if you don't remember that, then graph it. It's fine. Okay. So that's your special case number 2. Occasionally you'll say, ooh, they have all the same points. Okay. Because they are the same lines. That's what happens there. Okay. All right. So just to kind of show you some stuff, there are 2 other techniques other than graphing, and I want you to show you a little bit of both of these. So method number 2. Method number 1 was graphing. I don't think I actually wrote that anywhere. Let's see. Way back here, I think. Oh, I did. So it was 3 pages back on mine. I said solving by graphing. That was method number 1. I'm sorry, I didn't tell you that. So you could solve by graphing. Okay. That was method number 1. That was back when we found the calculator told me 12.8 was a point. Okay, that was method number 1. Now I'm on to method number 2, which is substitution. Okay, and I'm just going to tell you, substitution isn't my favorite either. It works really nicely when it works, but sometimes it's kind of a pain to deal with. So sometimes I'm just like, why bother? Okay, but here's what happens. We're going to have a system of equations. Let me give you an example. Okay, 3x plus 2y equals -2. And the second equation is 2x minus y equals -6. That's my system. Okay, I've got the little curly cues there to tell us that. Okay, so what the heck's happening in substitution? Well, we already know what substitution looks like, right? We substitute in a value for x. We substituted when we were doing derivative by definition. So what we're going to do here is we're going to solve one equation. We're going to solve one equation for one variable and substitute it into the other equation for that variable. I'll show you what I mean. Okay, but that's the idea going on here. You're going to solve one of the equations for one of the variables, and then we're going to substitute it into the other equation for that same variable. Okay, so here I am. I'm looking at this and I see I've got an x and a y. I've got an x and a y. They're the same variables. That's good. They're always going to be the same variables when I've got a system like this. Okay, well, not always, but for us, they're normally going to be. Okay, and I want to solve one equation for one variable. When I look right here at this second equation, I see that -y is by itself. I like that for solving for that variable because I'm not going to have to divide by like a 2 if I were to solve here for y. If I were to solve this one for x, I'd have to divide by a 3. And if I were to solve this equation for x, I'd have to divide by a 2, right, to get that variable by itself. That's what we mean by solve for one variable, is get that variable completely by itself. And I just don't want to do that if I don't have to. So I'm going to use this second equation, and I'm going to solve 2x minus y equals -6 for the y, because I think it's going to be the easiest one for me to solve for. Okay. And if you solve for one of the others, it's totally okay. It is not wrong. I just think this is going to be the easiest way for me. So I'm going to get the y by itself. So minus y equals, I'm going to subtract off the 2x, -2x minus 6. And then I've got the y equals, but it's got a negative out in front of it. So I need to divide by -1. And I'm going to divide everything by -1. It kind of works out nicely here because everything was negative. So y equals 2x plus 6. There we go. Okay. So equation number 2 is solved here for y. Okay, that's the first part. Solve one equation for one variable. We got that. Okay. So, and I just literally said this is number one and this is number two. It's nothing special. I just said the first equation, the second equation. Okay, so equation number two. But I'm not finished. It says, and substitute this into the other equation for that variable, for the y variable in this case, right? Okay. So I've got the second equation solved for y, and I want to substitute that into the first equation. So this is equation number 2 solved for y. I'm going to substitute it into equation number 1. I'm out of space there, so sorry. Equation number 1. Okay, so here was equation number 1. It's 3x plus 2, but instead of writing y, I'm going to put all this stuff is what we're saying. We're going to substitute right there. 2x plus 6. So instead of 2y, that's what equation number 1 says, 2y, right? I'm going to write 2 times, and this is all the stuff I just solved for y, right? Okay. 3x plus 2 times the y stuff equals -2. That's equation number 1, right? Equation number 1, but I've substituted in that stuff for the y. Okay. That's all I'm doing into the other equation for that variable. Well, it's not all I'm doing because now I need to solve for the second variable. So what it does for me when I do this substitution thing is I picked y value. You could have picked x value. It doesn't matter. But one of my variables here is going to go away, right? When I substituted in for that y value, I only have x and x now. There's no more y. So one of those variables went away, and now it becomes very easy for me to solve this guy the way we're used to solving linear equations, right? 3x plus, I'm going to distribute, that's 4x plus 12 equals -2. Okay, combine like terms, 3x plus 4x, that's 7x. I'm going to subtract this 12 off on both sides, so it goes away. -14, 7x equals -14. All right. And then last but not least, divide by 7. I'm just solving for the second variable, right? We know how to do that. Okay, so x equals -14 over 7 is a -2. Okay, so x equals -2. Solve for the second variable. Okay. Now, so I have a value for my x. Looking back at my original problem here, I had x and y. Okay, so is it enough for me to say, hey, x equals -2? No, Dr. Webster, it's not enough. We have to get a value for both of these. In fact, if this is a system of equations, we know these two lines are going to cross, right? And this is going to be a coordinated pair, okay? So I need a point. Need my y value. Not done yet. I'm almost done, but I'm not done yet. So where do we go to get our y value? Well, you can go to any of the upper equations that you want to, but I like this one, right? We solved it, y equals 2x plus 6. We've already got that. You can go there. But if you don't like that, you can put in your x in either one of these, and you would be fine, okay? But I know y equals 2x plus 6. That's one of my equations. I already had it. As long as I didn't make any mistakes as I was doing my work, I should be okay. So I'm going to plug in a -2. Y equals 2 times -2 is -4 plus a 6. That's a 2. Y equals 2. So I think my point is -2, comma 2. Okay. Solution for the system. How am I going to know? How do I know if this is a solution for my entire system? It's got to work in both of my equations, right? Both of those guys right there. Okay. So it's good to take a minute and go back and check these solutions, right? So I'm going to do it because I'm sitting here. Let's go back and look. We had 3x plus 2y equals -2, and we had 2x minus y equals -6. So I'm just going to plug it in and see. Let's find out. Okay. So if I had 3 times, I'm going to plug in a -2 there, plus 2 times, I'm going to plug in a 2 there, equals -2. Well, let's see. That's -6 plus 4 equals -2. Is that true? Yep, that one works. Okay. And then over here, I've got 2 times. And I'm going to put in a -2 there. And then minus, be careful with all these negative signs running around. Minus a 2 equals a -6. You see where my mind goes. I immediately see all those negative signs and I say, whoop. And I'm talking to myself as much as I'm talking to you guys. I say, whoop, be careful. There's lots of negatives. So it's 2 times a -2 for the x minus a +2 for the y equals -6. All right. So 2 times -2 is -4, minus 2 is a -6. Is that true? And the answer is yes, it works. So this guy works in both of my equations. I do indeed have a solution. Okay. All right. I'm going to give you one for you to work doing substitution. In fact, let's use one of the ones that we did earlier that we use graphing. So let's do the very first one we had. 2x plus y equals 32 and x plus 3y equals 36. We already know the solution to this one. We already did it graphically, but if we did it right, then doing substitution should also work. So push pause, do this on your own. I'm going to push pause. I'll work it out and we'll see if we match. All right. All right, here we go. Now, I'm going to say this before I get started. I chose to take equation number 1, the first equation, and solve for y. But in this particular example, you would have been just as easily, it would have been just as easy for you to take equation number 2 and solve it for x, okay, because it also is sitting there all by itself with no variable. I'm just kind of used to solving for y, so I did this one because it didn't have a coefficient in front of it. It's just a 1. If this had been a 5y, though, I would have totally solved for x in the second one because, again, if I don't have to divide, I don't want to divide. So if you chose to do equation number 2, you were perfectly legit and you should have still gotten the same answer I did. You would have gotten your y value before your x value, and that is fine. They should still be the same. So I took that equation, I solved for y. I took what I had, I substituted it into equation number 2, where I saw the y value. I plugged it in there. And then I solved for the x, and I got x equals 12. That's actually what we had the last time when we did it by graphing. And then I said, "Oop, I'm not done yet because I need a coordinated pair." So I plugged it back into equation number 1. I actually did the solved version, the y equals. You can put it wherever you want. And I got out an 8. And there is my point, 12,8, which is actually the exact same answer we got when we solved this by graphing. Yay, I love it when a plan comes together. Okay. So hopefully you did something similar to that. If you use the other equation and solve for x, it's fine. You should have gotten y equals 8 and then come back and plugged it in and gotten x equals 12 second. The answer will be the same even if you do the other equation. It doesn't matter. The answer is still the answer. Okay, the solution is still my solution. Okay, so that's the solution to the system. All right. So that's substitution. Again, I don't love it because it's a little bit cumbersome. It's a little bit clunky. I have to have one that I can solve for one of the variables. Sometimes I have to divide. It's bleh. I don't love it. Okay. So the third method number 3, is actually my favorite. Elimination. Okay. Elimination. And what are we going to do here? We're going to multiply one or both equations so that one variable goes away. Or in other words, it's what? Eliminated. Yay. Whenever I went through school, they called this the additive method, the addition method. They don't call it addition method anymore because sometimes you have to subtract. So they decided, addition is a little bit probably of a misnomer. It's misleading. So they say eliminate now instead. Just a little fun fact about how old your teacher is. Okay, so here's our example. So we're going to multiply one or both equations so that one of the variable goes away. And then we'll solve for the other variable. And then, of course, at the end, we have to plug in. So that process is going to be the same for like all of this. Okay, so here we go. My example is 5x minus 2y equals 12. 2x plus 3y equals 1. That's my system. And this is why I like elimination better. Okay. So if I had these two equations, substitution is not amazing for me, right? Because no matter which variable, no matter which equation I'm trying to solve for one of the variables, I'm going to end up dividing and it's not going to be pretty. Like if I tried to solve for x here, I'd have to eventually divide everything by 5, and these two numbers aren't divisible by 5. If I solve for y, I'd have to eventually divide by -2, and 5 is not divisible by -2. So it's just kind of ugly. It's cumbersome, that substitution thing. Same thing here for the second equation. These 2 and 3 are prime numbers. They don't go into each other. So they're mutually exclusive, so to speak, except for 1. They have 1 as a common factor. That doesn't help me. Okay. But elimination works so nicely here, okay? And in my mind, if I see right here, one of my y values has a positive and one of my y values has a negative, I will almost always say, let's eliminate the y value, okay? The y variable. And the reason why is because I'm going to add these together or subtract, but normally I add. And whenever I get there, I'll already have a pre-built in negative and positive, okay? So in my book, I'm going to eliminate the y value. Okay, that's the one. I like it. I'm going to get rid of it. Okay, so I'm going to eliminate the y value. And in order to do that, though, it's a little bit more work-wise at the beginning because again, 2 and 3 don't have anything in common, so because they're both prime, so I'm gonna have to multiply both of these equations. So I'm gonna say, "Hey, what does 2 go into that 3 also goes into?" They both divide evenly into 6, right? So if I turn this guy into a minus 6y and this guy into a positive 6y, then when I add those, they're going to eliminate each other. Negative 6y plus 6y is a 0. You'll see it in a second. Okay. But for right now, I say, hey, what do both of those go into? They go into 6. If I want 2y to become a 6, what do I have to multiply it by? 3. And so if I'm going to multiply this y value by 3, I have to multiply the whole thing because this is an equation. I can't just multiply one variable. So basically what I'm going to do is I'm going to distribute 3 all the way through. You could put it on the front. I just didn't have space on the front. I'm sorry. If you like it on the front better. Okay, I'm going to multiply 3 all the way through. So 3 times 5x is 15x. 3 times negative 2y is negative 6y. And 3 times 12 equals 36. Okay. And then what about this one? I want the 3y to become a 6y, right? So that'll reduce out. So I think, 3 times 2. Sorry, I'm just having a hard time writing today. 3 times 2 is going to make that guy go away. And again, I will distribute that 2 all the way through. You can't just multiply the y. You've got to multiply all of them. So this becomes 2 times 2x is 4x. 2 times 3y is a positive 6y. And 2 times 1 is a 2. And that's what I'm looking for right here. I'm going to add these two equations together. It's maybe something we haven't done before. But when I add these two equations together, the minus 6y and the positive 6y, those go away. I get plus 0, right? And what do we know about plus 0? We don't care about plus 0, right? Okay, so that guy is just going, that y value is just going to be eliminated. So that one variable goes away or is eliminated. That's what we're after. Okay, 15x plus 4x is 19x. Okay, 36 plus 2 is 38. Hey, this is going to work out very nicely for me because I've got 19x equals 38. And when I divide by 19, I'm out of space down there. I'm sorry. 38 divided by 19 is 2. X equals 2. All right. So that's kind of cool. The x equals 2. I need to go back. I said I solved for the other variable, and then I need to go back and plug in, right? Okay. Because why? I have the x value. I need the y value, right? That's what I hear you saying in my brain. You don't have a y value yet. You're right. I don't. Okay. So let's come back up in here. It doesn't matter. I'm going to go back to one of the originals. It doesn't matter which one. I'm going to pick the first one, but you could just as easily pick the second one. I've got 5. My x was 2. Plug in the 2 minus 2. I've got a y there equals 12. You could have plugged the 2 into the second one. It doesn't matter. Pick one. 10 minus 2y equals 12. I'm going to subtract the 10 off. Minus 2y equals 12 minus 2 is 10. I'm sorry. 12 minus 10 is 2. And then I'm going to divide by negative 2. Y equals negative 1. All right. So my value is 2, negative 1. That's my solution. Okay. So how can you check if you wanted to check? I don't want to go back to the first equation because that's how I got my y value, was using the first equation, right? So if I did my math right, it should always work in the first equation because that's where I got it from. So if you want to check your solution, you should go to the other equation. If you use the second equation to get your y value, you should go to the first equation because some of you might have done that. So here I am. 2 times my x value is a 2 plus 3 times my y value is a 1. Is that a 1? That's what we're trying to find out here. Well, 2 times 2 is 4. Minus 3, because 3 times negative 1. Is that a 1? Sure enough. All right. So, and then if you wanted to, you could take this guy and you could graph him, both equations. You'd have to solve for y, and you'd see, hey, it really is, the solution really is 2 and negative 1. All right. So you can totally do that if you would like. Okay. So that's the idea here. We're going to do, let's go back and do the same one we've done twice now. So my example is that very first guy. 2x plus y equals 32, and x plus 3y equals 36. And my directions are solve by elimination. So this is method number 3. Solve by elimination. All right, and let's do the same thing. Let's pause. You work it out. I'll work it out, and we'll come back and check each other and see what we got. We already know the answer for this, hopefully, right? It better be 12 and 8, right? I think is what we had before. Okay. So I'll see you in a minute. All right. This one's a little bit more in depth than the last one because when I go to eliminate either the x's or the y's, neither one has one positive, one negative. Both the x and the y, all 4 of those are positive. So I just chose to go ahead and eliminate the y value because that's what I'm used to. So when I eliminate the y's, what do I need to do? I'm going to multiply equation number 1 by -3, and I'm going to distribute that all the way through. That's my plan. So -3 times 2x is -6x, -3 times y is -3y, and -3 times 32 is -96. I didn't do anything to the second equation, so I just write it down the way it is. X plus 3y equals 36. And then I have negative values. One's a positive, one's a negative on my y's. So I'm going to add these. Negative 5x equals -60. And sure enough, that gives me x equals 12. And just very quickly, I plugged the 12 into equation number 2. 12 plus 3y equals 36. And I got, sure enough, y equals 8, which is the same value we've gotten for that solution, for that system of equations. We did it once with graphing, we did it once with substitution, we did it once with elimination. So on a test, I might say use substitution because I want to see you work through that process. Or I might say use elimination or something like that. And that's because I want to see that you know all the different methods. But in general, unless they tell you what method to use, or unless I tell you what method to use, you can do any method you like. Okay. And if I had my choice on most of these equations, I would be doing these like this. Okay. That's just the way I'm going to roll with it. Um, real quickly, let's look at the two special cases in the elimination method because I want you to see what happens. All right. And then we will be done with this material. On the application ends of things, you should see something in your homework where it talks about hey, what if you had a price function? What if you had a supply? What if you had a demand? Find the equilibrium points, find where these are equal to each other, that kind of thing. That would be a solution for the system, right? So we've actually already seen that kind of thing before, but you'll see it again in the word problems. So just be aware, you'll see it. Okay, let's go back and do this problem. X plus 2y equals -4. 2x plus 4y equals 8. Okay, we already solved this one. This was one of our special cases, but I want you to see what it looks like when we solve by elimination. And it also works with substitution, but I don't use elimination, or I don't use substitution that much. I use elimination a lot more. And so I just want you to see it so you'll be like, oh, that's what's going on. Okay. So this one was the one that we said was going to be parallel lines, right? Okay. So we should know, remember when they're parallel lines, they run side by side forever. They never cross. So this one was no solution. So I know up front, that's what I should be looking for, is a no solution. What I want you to see is, what does that look like when you're not graphing it? Okay, so let's see. We're going to eliminate. Let's do the x values. I haven't done any eliminating x values yet, so you can do it. I just am kind of hung up on y's a lot. So when I look at this, the x and the 2x, I see, hey, if I eliminate the x values, they're both positive. This is a 1 out in front. This is a 2 out in front. I can multiply this first equation by -2. Okay. That would give me -2x, and that would give me a positive 2x on the second equation. And that would go away, right? Those would eliminate. So I think I'm going to distribute through a -2 here. So -2 times x is -2x. -2 times 2y is 4y. And -2 times -4 is a positive 8, right? Okay. So the first equation, I'm just checking my negatives up. See, here it is. -2x, this was a -4y. See, that's why I go back and check my negatives. Equals a negative times a negative is a positive. Okay. So I've got -2x, -4y, positive 8. Okay. And then when I go to do this, I've got 2x and 4y equals 8. That's weird, right? Like, hopefully you see what just happened. I was trying to eliminate the x's. I made it so that these, when I add up, those 2 will go away, right? That's a 0. That's what I was after. But inadvertently, what happened was I've got a minus 4y and a positive 4y. And what happens there? Negative 4y plus 4y is 0. And then here I've got 8 plus 8, that's 16. So what I'm seeing here is I've got 0 plus 0 or 0 equals 16. Is that a true statement? That's a false statement, right? And what I like to say is I like to ask students, when is this going to work? When do we see 0 equals 16? Never. Okay, it's never going to work. 0 does not equal 16. So whenever I see something like that, 0 equals 16 or 5 equals 0, or it could be something weird like 3 equals 2, whole numbers or fractions or whatever, they have to be equal to themselves, right? Like when we checked those solutions earlier, it had to work out that they were the same number on both sides. This is not true. 0 does not equal 16. So this is a false statement, and this is no solution. So when you're working along and all of a sudden everything falls out, that's what happened here, right? Everything just dropped except for the constant, and I had 0 equals 16. Oop, that's not true. That's a no solution, guy. Okay, so that's the special case where they were parallel lines. Remember, parallel. Okay. And then there was the other special case, so just be aware. When you get one of those false statements like that, it's no solution. Those are parallel lines. The second special case was 2x plus 4y equals 8. And x plus 2y equals 4. And remember, if you will, that we're going to solve by elimination again. But when we did this by graphing, if you'll remember, this was an infinite number of solutions. Okay, and that was because it was an infinite number of solutions because it was the same line. You remember that? Okay, we just talked about it a minute ago, so a few minutes back. So it was the same line. So when I go and I look at this system of equations like this, and I try to eliminate them, let me do the same thing. Let's do it on the y value this time. Okay, and I say, hey, a 4y and a 2y, if I multiply this bottom equation by negative 2, and again, we're going to have to distribute, right? Distribute, distribute, distribute. That's fine. We'll get it distributed. But if I multiply 2y times negative 2y, that would be negative 4y. And 4y would cancel, right? They would drop out. Okay, so that's what I'm after. The first equation, I'm not doing anything to it. 2x plus 4y equals 8. And then here it's negative 2x, negative 4y, negative 8. Now hang on a second. I was trying to get rid of the y values here, right? I was trying to eliminate those, and that sure did happen. Yep. Those went away. Good. But what else happened? And that was not what I was trying to do. 2x and negative 2x also go away. So 0 plus 0, because I'm adding these out, right? 0 plus 0 is 8 plus negative 8 is 0. Oh, hang on a second. 8 plus negative 8 is 0. 0 equals 0. Is that a true statement? That is. In fact, when is 0 equal to 0? Always. 0 is always equal to 0, right? Okay. So that means no matter what number I put in here, I'm going to get something equal to itself. I'm going to get a true statement. Always. Okay. That's when I know, oh, this is the same line because it's always true. That's when any solution works in both. because they're the same line. They're just written a little bit differently, but they lie right on top of each other, right? They're on top of each other, so it's the same line. Okay, so sometimes we'll see it like that. We'll be like, oh, they look a little bit different, but hey, I know these happen to be the same line. And we'll say, oh, infinite number of solutions. There is kind of a weird way to write that, the infinite number of solutions. You'll see it in the homework that they'll be like, hey, is this true? Basically, what they'll say is they'll say something like, let x be any real number. Sometimes they'll use z for integers stuff. Oh, sorry. For integers and stuff like that. They'll say, let x be any real number. So y equals, and then sometimes they'll solve it for the y value and have it in terms of x's. I don't really care about that so much. Your homework does. So just realize that if they say, hey, if x is any real number, then the y would be, you'd have to solve this for y. And I just don't want to do it right now. So, but you could get there. Actually, we have it solved for y back in the graphing one, right? So let me find it real fast. Sorry. I just don't care to solve it for y again because I'm so done with that by now. Okay. So either one of those, you would have y equals -1/2 x plus 2, right? That's what we got. Okay. So, and the x can be any number because it's an infinite number of solutions. If you put in x equals 1, you get a certain y. If you put in x equals 2, you get a different y. So you'll see them, they'll be maybe a little picky about that, the way they write that in the homework, but for a test, all I care is, hey, if you got that far and you know it's infinite number of solutions, I'm gonna be so thrilled with you. So, all right, that's it for this section. Good luck with the homework. Let me know if you have questions.